calculus syntax to Haskell syntax. Haskell expression is just a humble extension to the lambda calculus to include the constants, infix operations, data constructor, let binding, and case expressions. Where in the case expression, we introduce this pattern P, where pattern can be either a data constructor pattern, a pattern variable, or a constant variable. For now, for simplicity, we treat infix operators simply just for arithmetic operations such as plus, minus, multiplication, and divisions. And they have a different treatment compared to the function application. Another point to note is that we do not allow duplicate of pattern variable in a pattern. So in other words, sometimes people refer that is a linear pattern restriction. For example, people are not allowed to write cons x with x or cons with y and y. Another simple notation to make the syntax more concise is that we use a upper bar to denote a sequence of objects. So operational semantics. We first consider function application. We have mentioned earlier on that Haskell operational semantics is following the normal order reduction. So besides the alpha renaming rule, we want to make our beta reduction rule more syntax driven. We consider two different application rules, app1 and app2. In app1, we see that the first sub-expression is already in a lambda abstraction form syntactically. So over here, we're just applying the old beta reduction rule by constructing the substitutions and apply it to the body of the function. Then in the app2 rule, we no longer have the information where the first sub-expression is in a lambda abstraction syntactically. We then need to apply the deduction system to make E1 to reduce into some expression E1 prime, and if it's not yet in a lambda abstraction form, we can then apply it again and reduce it further. So the system here is basically a models after a deduction system where we write P1 over P2 to denote a deduction rule, and it reads as if P1, the premise, is deducible, then P2, the conclusion, is deducible. Intuitively, these two app1 and app2 rules together will form an evaluation strategy, meaning when we see a function application E1 applied to E2, we keep evaluating the function expression E1 until it gives us a lambda expression. Hopefully it's lambda x goes to E1 prime. Then we apply E2, which is the actual argument, to this lambda function via the beta reduction rule. Consider an example. We consider evaluating this Haskell program. We first apply the app2 rules to this expression because this first sub-expression over here is not yet explicit in one single lambda abstraction form. So we consider reducing this part. And now we consider this sub-expression, and this is already in the regex form syntactically. We can apply the app1 rule and reduce it and constructing the substitution and apply it to the function body, and that will give us a abstraction of lambda abstractions, w goes to w, and this whole expression together now is again in the syntactic regex form. We can then apply the app1 rule to construct the substitutions, where we go into substitutes. This is our E2 with all the occurrence of the variable w into the body. Okay. By applying the substitution rule, now we get back this is the result, and again this is a syntactic regex. We can apply the app1 rule to construct these substitutions. Finally, we get back our final answer, which is a lambda x goes lambda z go to z. Rules for the infix operator. So which is simple, we only have three rules. So in case the both opera of the operator are constant, we can simply just call the underlying operation to perform the actual arithmetic operations. In case the first operand is a constant but the second operand is not yet a constant, we then have to reduce the second operand E2 into some E2 prime. The third rule says that if the first operand E1 is not yet a constant, then we apply the deduction rule to reduce E1 to E1 prime. Expressions is very straightforward. In case we see an expression is a let binding, let x equals to E1 in E2, we can simply create a substitution to replace all the occurrence of x by expression E1 in E2. For case expressions is more involved. For case rule to work, we need to define a subset of the expression called the weak normal form, or in some other textbooks or reference is called weak head normal form. So we use this notion E cap to denote the Haskell weak normal form. So a weak normal form is either a lambda abstractions or data constructor or a constant. And now we formally introduce the notation for the substitutions, which is denoted by the big theta. So it's actually a order list of substitutions individually. Okay. For simplicity, we use the Haskell list syntax here. Okay, there are two case rules. Okay, the first case says that if the case conditional expressions is already in a weak normal form, okay, then we can simply check for out of all the pattern P1 to Pn and looking for a particular Pi such that this E cap, which is a weak normal form, can match Pi and producing a substitution theta I. And in addition, for any other Pj that is preceding Pi, which is probably you can say that well syntactically is on the left hand side of Pi, and this E cap, which is the conditional expression in the weak normal form, does not match any of this. So this is to guarantee that our Pi is the first ever matchable pattern in the entire set of pattern alternatives. So once we have this theta I, we can apply it to the EI to carry on the reductions. In the case rule 2, our conditional expression E is not yet in a weak normal form. We then apply the deduction rule to make sure that E will reduce to E prime. So one point to note is that whenever we produce a match, okay, whenever using a match to produce a substitution theta I, there will never be a duplicate in theta. Okay, this is because in the earlier slide we were saying that Haskell syntax disallowed non-linear pattern, meaning that there's no duplicate variable patterns in Haskell syntax. So this will always guarantee that our theta I would always has no duplicate. Next, we're going to consider how this pattern matching rule are defined. Matching rules. The first rule handle the case for data constructor pattern. We are matching a data constructor expressions with a data constructor pattern, and we have to guarantee that all the number of E1 and En to En, which is the argument to this data constructor, should agree with the pattern. Okay, they should have the same number, and for each of the EI would match the Pi sub-expression and producing a theta I for all I starting from 1 all the way to n, and as a result we are producing a bigger substitution by simply concatenating all these sub-substitution together. The second rule handle the case of constant pattern. So we only allow the same constant to match the constant pattern, producing the empty substitutions. The third rule handles the variable pattern. Any expression will match a variable pattern and producing a substitution that substitutes x with the expression E.